Well, good morning. We're going to be uh, beginning today in our traversal of a new and a very important chapter of this book, Sheaf Theory Through Examples, particularly specifically chapter 4, which focuses on topology. Uh, I'm really excited to, to teach this material. It's reasonably new to me as well, and I'm still learning some in this area, but it's a topic which has direct bearing on the topic of sheaves. I mean, sheaves are defined over topological spaces, so they involve data to some degree characterizing behavior over on a topological space. And the notion of a topological space and its topology and the relationships captured in that topology are therefore of foremost interest when it comes to our focus on sheaves and pre-sheaf variants. This material is, I think, likely to be new to pretty much everyone in our lab. I think UJ has encountered some ideas from topology before, but for many of us, it's quite new, and it really ties in with many of the categorical ideas that we've been discussing. Indeed, category theory really arose from algebraic topology, from the broader topological space, topological area. And we're going to be approaching it heavily categorically within this course. With that being said, there are aspects of its exposition which have a great deal of context to them, both within the book and externally. I find when it's taught that may not be as familiar to people in this group. And I want to see if in traversing this chapter in our discussion, we can emphasize some of these points and ultimately link them up to similar categorical ideas. So topology is sometimes called rubber sheet geometry. It's sometimes classed as lying within geometry, but if so, it's a type of geometry that's very foundational, that's very, very basic in its assumptions and very powerful in general in its application. I like this rough definition of topology that I picked up from Richard Southwell, whose many lectures folks here may be familiar. He defines this the study of properties of geometric objects preserved under, so honored by, continuous deformation. And when we say continuous deformation, this gets this idea of a rubber sheet. We can stretch things, but we can't tear, we can't cut. We can't open a hole or indeed close a hole in so doing. And this definition reflects the fact that it's dealing with more basic things. And indeed, the most fundamental definitions of topology or topological space that we'll be dealing with don't depend, for example, on having a metric by which we measure distance between points in space, for example. But we can still retain a sense of points being close if you think about a rubber sheet, the rubber sheet being stretched may take 2 points that are close earlier, and it may stretch them a little bit further from each other, but they're still close comparatively in the space. Even though we don't have a fixed type of distance, it's been something which has been distorted. We retain closeness, and indeed will retain other features of the space, like the number of holes associated with it, the number of loops around those holes, for example. And there are these sets of fundamental properties that are retained by these continuous deformations that form the study of topology. Now, for us, I wanted to hit on a number of key sort of concepts and themes. One is we're going to be talking about the most basic definition of topological space. There are many successive layers we can add on to that definition to equip those spaces with additional structure. For example, the presence of a metric, or for example, the properties of a vector space. We can assume characteristics of a manifold, perhaps an infinitely differentiable manifold, for example. And those each build extra structure on. But at the end of the day, all of these are going to be reflective of a set equipped with some extra structure. And we're going to see that a topology is more than a set. It does depend on a set, but it's a set with extra structure. In our case, structure that reflects relationships involving things like intersection and unioning. And I want to emphasize this, that from a categorical standpoint, here, spaces will be defined by operations on set. Just like we say that the structure in a category comes from morphisms and the rules for composition of morphisms, the unitality that, you compose an identity morphism, a unit morphism, as it were, with another, you get that other morphism back. There's structure captured there in these morphisms in the rule for composition that define the structure of the category. Structure spaces here are defined by the operations and the relationships between things that, if you take set A and set B and you intersect them, you get set C, for example. But there's logical consistency. There are certain axioms that have to be obeyed. We're dealing with a topology within the context of a topological space as being closed under certain operations, intersection. So finite intersection and arbitrary unioning. So there's this logical consistency for it to be a nice space. There's a notion that Rosia emphasizes in the book of a neighborhood, and sort of topology is capturing neighborhood information. And I'm going to try to emphasize why this comes out of topology, because it's in the notion of topological space we'll be dealing with, even at the most basic level. Because you can approach it from a very abstract, high-level perspective, and it's not obvious where neighborhoods come into the picture. You have a set of sets, and they're closed under a finite intersection and arbitrary union, and the empty set is in there, and the full set, but it's not clear, like, where's the neighborhood? Where's locality? Where's connectivity? Where's things being close to each other? Two things being close to each other as opposed to being compared to being distant from each other. And I'll try to show ways that can come in to even that most basic element of topology that we'll work with. Now, something that's actually quite important for us in our work, and indeed in practical application of sheaves and indeed pre-sheaves, concerns combinatorial descriptions of topological spaces. So the spaces we can put pieces together. And we'll see that abstract simplicial complexes, or simplicial complexes that are embedded simplicial complexes, embedded in some space or some broader ambient space, or that are composed more abstractly of vertices, edges, triangles that are two simplexes, tetrahedra that are three simplexes, etc. Those are combinatorial descriptions. We could sort of add things in and describe it as being made of these parts. And there, as well as elsewhere, including in the book, there's quite a bit of discussion about the relationship between a region and its boundary. So maybe this is a edge, and the boundary refers to its two vertices. Or maybe it's a triangle, and its boundary refers to the three edges on its side. And there's the structural relationship between a sort of component of the space and its boundary that will end up being of real importance with sheath. Okay, so I'm going to try to bring out some of these concepts and in this discussion and in office hours, etc. So I noted the rough definition of topology, study of these fundamental properties of objects that are preserved under continuous deformation, rubber sheet geometry. Now, in category 3, we talk about structures equipped with different levels of structure. We see this in two categories. You see it in context of things like going from sets to going to categories, going to two categories, etc. In our context, sort of most basic notion is going to be familiar to us of sets. We've been dealing with that for a long time. But up from there, in terms of structure, is the topological space. It's a set. It involves a set, for sure, but involves relationships between different subsets of that set. And those relationships give it structure. And that structure will be of great importance in understanding sheets. Those will be the places over which data can live, behavior can be realized. And then there's sort of topological spaces where we add a metric to measure distance. And the metric has to be the distance between any 2 points has to be greater than or equal to 0. The only point for which it's if we take x and y such that the distance is 0, then x must equal y. The distance from x to y is equal to the distance from y to x. And it has to honor as well the triangle inequality, etc. So we have metrics with topological spaces. And then we can add in structures of manifolds, these kind of lower dimensional surfaces that look flat at any given place. They may look flat, just like the surface of the Earth looks flat, even though it may be round. Even though it's round, even though it's a sphere, it looks flat at any given point, and it's a feature of manifolds. And those can exist in certain dimensions, and we can have topological manifolds, and we can have smooth manifolds. For example, manifolds with arbitrary differentiability, like it has only smooth contours within it, and some additional structure with Riemannian manifolds. But my point here is not to go into each of these. Indeed, we'll be dwelling heavily just on topological spaces. But the point is that each of these equips what was viewed earlier with added structure, and it has extra properties that come out of that. And you'll find a lot of attention in topology at these higher levels of structure. A lot of the examples you'll see in topology will be dealing with metric spaces or manifolds. And those are interesting, but they're not the focus of this course. However, the methods that we define with sheaves for topological spaces carry over to all of these, because these add structure. They have the structure requisite needed to define sheaves. Okay, so what is this most basic notion of a topological space? Well, to understand it, we need to talk first about a topology. And a topological space will be a pairing of a set and a topology on that set. So a topology on a set X, don't get caught up in it being a manifold, don't get caught up in it being having distance and all. It's just a set. And a topology is a collection of subsets of X, tau, that has very specific properties, that honor certain axioms, that obeys certain axioms. What is this? This subset of this set X. Excuse me, it's a collection of subsets. Subset. It's a collection of subsets, tau, of X. What are the that obey these axioms? What are the axioms that obeys? Well, it's some subsets of X, and one of the things that's always present is the empty set. We'll see why that comes out automatically of a later one. It's the empty set. So the empty set is always an element of the topology tau. X itself, the full set, is also guaranteed to be in the topology on set X. So I told you the topology is a collection of subsets of X, and X is one of the subsets of X, just like the empty set is. So both of these are guaranteed to be in a topology in set X. And we'll see, in fact, that just those two form a valid topology themselves, called the indiscrete topology. But beyond that, the topology has to be consistent with the fact that whatever is in it, whatever subsets of X that are in this topology tau, their union of any number of them, any number, could be a finite number, could be a infinite, countably infinite number, it could be an uncountably infinite number of the subsets of X that are in tau. The elements of tau are subsets of X, right? The union of those, however many you combine, has to be itself an element of tau. The union of all these subsets of X, for however many you want a union, that's also an element of tau. And so the union of all these elements of tau, I should say, which are subsets. And the finite intersection of elements of tau, these subsets of X that are in tau, their finite intersection is also guaranteed to be in tau. So if we have two subsets of X, A and B, their intersection, A intersect B, two subsets of X, A and B that are in tau, then their intersection of A and B is also in tau, is in the topology. Now, these items in the topology, each of them being a subset of X, each of these elements of the topology, tau, is itself a subset of X. Each of those is called an open set of the topology. And the collection of all of them are the open sets of the topology. Now, we'll go through an example here. But I want to emphasize that we're describing this construct of a topology on X in terms of the relationships involved. That if we have two elements of tau, two subsets of X, there are elements of tau, their intersection is in tau. Or if we have, this infinite collection of elements of tau, different subsets of X, and we take their union, that's also in tau. So this is going to seem a little bit abstract. Maybe I'll go to some examples. Okay. So here are some examples. I'm interested in people's feedback on this. I've written empty set here as open, close, curly bracket. Some people like phi. That's more common, but if I decide to write it there just to lower confusion of it with a Greek letter or 0. Okay. So for example, does this obey the axioms of the topology? We have the empty set. So suppose X, the set. So we're considering a topology on a set. What's the set? 1, 2, 3, 4. We're going to call the topology tau. If these are the elements of tau, is that a valid topology on X? We have empty set here, we have all of X, and we have 1. Is that a valid topology? And so Meti says yes. And how did you realize that? What are you thinking about? Empty is in there. X is in there. Okay, good. And the union of any two things in here, indeed, any number of things. Let's suppose we take union of empty set in itself. Well, that's in there. Union of empty set in 1. Well, that's in there because that's just a set of 1, right? Union of empty set in 1, 2, 3, 4. That's in there. Union of 1, the set of 1 and the set of 1, 2, 3, 4. That's in there. The union set of 1 in itself. Yes. Any combination of unions of these will be in there. So this is, in fact, a valid topology tau on X. Is this a valid topology on X? Yes, by the same token, mutatis mutandis. Okay. How about this one here? Is this a valid topology? No. And why not? What would be an example of something that needs to be in here, but is not right now? That for this to be a valid topology, if these are elements of tau, what else needs to be in tau? 1 union 2. Yeah. So the union of the set 1 and the set 2, which is the set containing 1 and 2, should be in here, but it's not, right? So this is not a valid topology. This is not closed under arbitrary union. We take union of these two things, it's something outside the set, right? that union of these two things is a subset of X, but it's not a subset of X in this putative topology, this claim topology. So this is not a valid topology on X. How about this next one? Yeah. Okay. So let's test it. By the way, we earlier we were a little bit glib. We didn't check the intersection properties of these. We should have checked the intersection, right? Remember, it has to be closed under intersection as well, of finite intersection and arbitrary union. So finite intersection of 1 and 1, 1, 2, 3, 4 is 1. Of 2, 1, 1, 2, 3, 4 is 2. Okay, for this one, is it closed under union? Arbitrary union? Yep. Is it closed under intersection?
I don't think so because of the set of 1, 2, 3. Because there's no set. Oh, wait. Yes, I think so.
It is closed under intersection. If you take the intersection of 1, 2, 3, 1, 2, what do you get? 1, 2. Take it of 1, 2, 3, and 1, what do you get? 1. 1, 2, and 1, what do you get? 1. Take it of 1 and empty set, what do you get? Empty set.
It's a clear hierarchy.
There's a clear hierarchy. Yeah. Yeah. Yeah, there is. So this actually is a valid topology. How about this one here? Is this a valid topology? Sorry, the intersection of this set of 2 instead of 1 and 2 will be 2, right? Is that a valid topology? Actually, is a valid topology. How about this one here?
I believe so.
That's the same reason as the one before.
Mm-hmm. Mm-hmm. So first of all, sanity check is empty set. There's X, all of X there. Yes. It's the union of any number of these present. Union of none will be empty set. Union of 1 and 2 will be 1, 2. Union of 2, 1, 2 is 1, 2. The only one 3 is grouped in here, but that's not a problem per se. You intersect this with this, you get 1, 2. That's in here. Intersect this with 2, you get 2. With 1, you get 1. With 1, 2, 3, you 1, 2, 3, 4, you get 1, 2, 3. So I don't see a problem with this. Does anyone disagree? Am I missing something? Okay, this is actually a repeat, I think, of the earlier ones. So, what if I said, just to make it, to actually use the line to some effect, what if this were 1, 3? Would that be a topology?
No, because the union of
Yeah.
2 and 1, 3 is not in there.
Exactly. We need 1, 2, right? We don't have it. Yeah. Um, how about all of these? I'll give you a hint. There's 15 of them here.
Do not have the union of 1, 2, and 1, 3.
1, 2, and 1, 3 is not present. 1, 2, 3 is missing. Yeah. You can tell that because how many would you expect if it has all combinations? To be 16, right? Because for each of these 4, you either have it or you don't. So it's like having a bit for each of these. So there's 2 possibilities for this, whether it's present or not, whether it's present or not, whether it's present or not, whether it's present or not. So it's 2 to the 4th, which is 16. So it would need to be 16 of them here. And this is all 16. Okay. So this may seem a little bit arbitrary, but it's far from arbitrary. There's deep reasons for these rules. And there's also intuitions for why these rules link to this notion of rubber sheet geometry, etc. I will note, as Rosiek does in the book, that this first rule